So in this video I'm going to look at spectrometry, or how we take measurements from stars using their light. So we're going to take a look at in this video at how we can actually work out what stars are made of. And to do that, what we're going to need to understand is the different types of spectra that we can get. We're going to need to understand why elements can only absorb or emit certain wavelengths, and then we can use those two things put together to explain what's in a star. Okay, so let's get. So previously we've talked about the birth of stars, we've talked about the death of stars, and we've talked a lot about the different reactions happening in stars. So hydrogen fusing to form helium, helium fusing to form carbon, and carbon fusing to form lead. But we've actually not seen any evidence of how we know that. So how do we actually know these elements are present in stars? Well, spectrometry is our method of doing that. So we look at the light we get from stars and we can tell what the stars are made of. And we'll look at in this video how we do that. So the first thing to understand is what we should be seeing from a star, because that's the starting point here. So we know from previously that the sun is modeled as a black body, which means it absorbs and emits all the wavelengths in the electromagnetic spectrum, some in larger quantities than others. So if we use a prism to split up the light, when we look at the visible section, we should see all of the colors in that because all the wavelengths are being emitted. However, what we find is actually some wavelengths are missing, which we see in the form of black lines when we split up the visual spectrum. So the next kind of spectrum we're going to look at is called an emission spectrum. So we found these by heating up elements here on Earth, and what you'll see is that these elements give off very specific wavelengths of light, and these happen to match up with the black lines we are seeing in absorption spectra. So in terms of placing where this knowledge goes, you will have probably in chemistry seen flame tests where you've seen different elements turn different colors when you put them in a flame. So that is an example of an emission spectrum. So we see a specific color because it's a mixture of specific wavelengths of light being emitted. So why do we get these very specific wavelengths when we heat materials, or missing wavelengths when we look at the light from hot materials? Okay. So to explain why only certain wavelengths are emitted or certain wavelengths absorbed, we need to build a quantum model of our atom. So the quantum model of our atom says that essentially electrons can only occupy certain energy levels. And you can see those on the left. They're given the different quantum numbers from n equals 1 at ground state up to n equals infinity when it's ionized. And we can see that each level has a different amount of energy associated with it. So what happens when we heat a material is electrons gain enough energy to move up to the higher energy levels, and that process is all called excitation. So the energy levels n equals 2 and above are known as excited states. But being up at an excited state is unstable. In any situation, having a lot of energy is unstable. So what happens? It de-excites back down to ground state, and it can take various different paths to get there, but it always ends up at ground state, which is given the quantum number n equals 1. So what we found was that the total energy electrons have at a given level, which you can see on the left next to each energy level, is linked to the ionization energy of the atom. So if you know the amount of energy it takes to excite an electron from ground state to ionized state, you can figure out how much energy each of the quantum levels has as well. So this is how we can start thinking about why we get specific wavelengths. So, as every element has a unique number of protons and electrons and has therefore a unique electric field, every element has a different ionization energy, and that means that every element has different energy levels in it. So because they all have different energy levels, the gaps between the energy levels are unique to each element, which means the photons emitted by each element are unique to each element, which is why we get the different colors when we heat different materials. Okay, so that's why we get the emission spectra. So you might ask at that point, well, don't those photons get re-emitted when the atoms de-excite? And yes, but actually when they de-excite, they get emitted in all directions. So although all the light was heading towards the Earth, some of it, when it's absorbed, is radiated in other directions. So we get lower intensity of those particular wavelengths. So going back to what we had before. So the photons that are absorbed by the atmosphere of the star are re-emitted in all directions. That means the intensity of those wavelengths coming towards Earth is much lower than those wavelengths which weren't absorbed, which is why we're getting the black lines. So the black lines don't mean we're getting no light, it just means the intensity is much, much lower. And because we can measure emission spectra here on Earth, all we have to do is compare our black lines to the emission spectra, and we can figure out what a star is made of by looking at the wavelengths that are missing from their spectra. So that finishes this video looking at spectrometry. If you look through these different things, this is what you should be able to do at this point. If you're looking at these and you're not sure about them, this is the point to go back and have a look at those sections. But thank you very much for taking the time to watch.